Hi everyone, today we're going to talk about regression with exponential models. Let's start by looking at a few graphs. First, I want you to look at what type of graph do you think is displayed in the consumer fireworks revenue, looking at the red firework, which looks at consumer spending. So would you call that linear increasing, linear decreasing, exponential growth, or exponential decay? When we're looking along this graph, I think we can see it grows pretty consistently. It's not going crazy, it's pretty slow, and I would call that linear increasing. How is this data increasing? We have the total assets of SLM Corporation, which is Sallie Mae, from 2010 to 2019. When you look at the growth, is it linear increasing, linear decreasing, exponential growth, exponential decay? Looking at the data, we can see there is a big increase of growth as we go. So it's not staying the same, it's not increasing by the same amount, it's increasing by higher and higher numbers every time, which says this would be exponential. This next graph has a lot of information, but I want you to pay attention to the blue that's highlighted. This is the number of landline and mobile connections in the United States from 2010 to 2015 by type of household. So the household that's highlighted is households without children that have landline and wireless. So we've gone from 62.2% to 58.8, 56.1, 52.8, 47.3, and 43.9. So do you call that linear increasing, linear decreasing, exponential growth, exponential decay? Definitely we can see these values are going down from 62, 58, 56. But the drop is not exponential. It's not a huge drop. It's close to a similar drop. This is close to 4. This is 2. This is 4. This is again close to 4. This is also close to 4. So most of the time we see about a 4% drop from year to year. What we would want to call that is linear decreasing. Let's quickly look at y equals 2.104 times 1.479 to the x, and I've shown you three graphs. Which one of these would represent our exponential equation? How I would decide is first think the 1.479 is growth. It's bigger than 1, which means it can't be c. C looks like it's decaying. When I look at A and B and I'm trying to decide, well, we can see they both start at about 2, but the difference between A and B is the shape of the curve. Exponential should curve up and B curves down, so we know our answer this time should be A. Let's take a quick look back at our values, which was our correlation coefficient. We're still going to use our values to find the strength of the relationship. Values close to 1 or negative 1 will be strong correlations. Values closer to 0 are weak correlations. When you're doing your comparisons, if you had to compare 0.9 to 0.7 to negative 0.3 or negative 0.95, and you had to say which one has the strongest correlation, the negative 0.95 would be your answer. When you're looking at correlation numbers, it doesn't matter if it's positive or negative, it's close to 1 or negative 1 that you're looking for. So let's look at finding R without actually doing a regression. In this chart, I have the values of 3.6, 9.40, 15.80, 23.121, and 37.215. I'm going to take those values and I'm going to plug them into Desmos. We start by adding a table. I can put in my values of 3.6, 9.40, 15.80, 23.121, and 37.215. This time I was using the tab to move from cell to cell, so it would move from 3 to 6. It goes from X to Y, and then from Y, when I hit tab, it comes back to X. So if you want to fill in line by line, like row by row, use the tab. That'll get you there. Now, I'm not going to do the linear regression like we've done before. Instead, I'm going to type in CORR. I want to show you COR was in italic, so that just looked at Desmos saying, I see you put in some letters. When you put in CORR, Desmos recognizes a command, and that command is correlation. But it needs to know what are you trying to correlate. So correlation says we're trying to tie two things together. We're trying to see a relationship. The two things we want to relate are x1 and y1. So I'm going to put a parenthesis, x1, comma, y1. So now they've looked at the relationship between these two numbers, and the value that I got out was 0.999. That's a great correlation. It's really close. If I hit the zoom fit, you could see those numbers and it looks linear. This time I put in 3, 230, 9, 5, 15, 800, 23, 12, 37, -2, and 32, 411. Now look at these values. They kind of make like a little shape, maybe a geometric shape over here, but I can see they really aren't lining up at all. So we shouldn't be surprised when we type in CORR with X1, Y1, we're not going to get a strong correlation. I got -0.13. That's pretty close to 0, which says this is not a strong relationship between these two numbers. The value V of a stock 2 years after purchase is summarized below. At time 0, it was worth $1,500. In 2 years, it was worth $1,785. In 5 years, $2,310. In 8 years, $3,011. And in 12 years, $4,200. We want to find an exponential regression equation for the data. When we find it, we are going to round A to 2 decimal places. We're going to round B to 3 decimal places. Then we'll use our formula to find the value of the stock in 15 years. And I said I want us to do an exponential regression, so we're going to type Y1, click on the tilde, and we say A, B to the X1. Really important when we're doing this, you need to hit the log mode. Log mode has Desmos use the same kind of calculation that programs like Excel or Texas Instruments would use when they're doing their statistical analysis. So super important that you hit that log mode to get the answers correctly. Also, when I hit the log mode, it makes the R value pop up. Watch, if I take the log mode away, it only has R squared. Look at the value of A, it says 1507. When I hit log mode, the value changes to 1503. So really important that you keep that log mode on. Now when I look at it, it says A is 1503.07, and we said do 2 decimal places, and then B says 1.0898. Now we said 3 decimal places, so 0898, that's 4 decimal places. When I round up, it's really going to round it over to 1.09. Our formula for V is 1503.07. Then our B is 1.09 from our rounding, and then we're going to write to the T because we're using T for time. If I ask you for the growth rate, remember that you are going to subtract 1 from the 1.09. So 1.09 minus 1 says 0.09, which is 9%. So pretty good investment if you can get a 9% return. Then we want to do a projection of what will happen in 15 years. In 15 years, we have 1503.07 times 1.09 to the 15th. This gives me a value of $5,474.91. Now, notice that I did this value on the slideshow. I didn't do it in Desmos, and there's a reason for that. We rounded. And if I go back to Desmos, and I'll put in 15 just to show you that it's slightly different in answers. If we did y equals AB to the 15th, because we want to know what happens in 15 years, Desmos would give us 5,460.17. Now, Desmos is more accurate because we didn't round, but you always have to do what your homework says to do. So if your homework says round to this many decimal places and then figure out what's going to happen in the future, make sure you don't use Desmos to get the answer. So what are we doing when we're doing linear regression or exponential regression? We're trying to figure out a relationship, and we're trying to see if 2 things are connected or not. If we get our value really close to 0 or not close to 1 or -1, we would say these 2 things aren't tied the way we thought they were. What we have in this example is the average cost to attend a U.S. university by institution type, and I started with a public 2-year university. What does that mean? That means a community college. We can see by year the average cost to attend. In 2013-2014, the average was $10,781, and we see that that value is slowly going up. For 2020-2021, the average was $12,850. We're going to put this into Desmos, and we're going to decide, is this an exponential or is this a linear regression? Like, what relationship is there? So we're going to run both sets of numbers. When I put the numbers in, that 2013, 2014, that's not really going to work. So we're just going to say we are starting at 0, and we're going to call this 1, 2, 3, 4, 5, 6, and 7. So this will be years after 2013. So if we had to go back and make some other adjustment, or we want to make a prediction in the future, we know we're going to do years after 2013, but we're going to take this data, throw it over to Desmos, and do some comparisons. So I'm going to start my table by typing 0, 1, 2, and then if you watch, it's going to start popping up 3, 4, 5, 6, 7. That saves me a little bit of time, and then I can type in the values for my averages. Once I have all the values in, I am going to hit the zoom so I can see the relationship and see what it looks like. We're going to do both of them. We're going to do both linear and exponential. So I'm going to type y1 is approximately, we'll start with a linear ax1 plus b. Then we'll also try y1, and we'll say is approximately ab to the x1. And don't forget that really important step of hitting log mode. So what do I want to look at? I want to look at the R values. So the R value for the linear is 0.9966. The R value for the exponential is 0.9961. It's a slight difference, but the line is actually better than the exponential in this case. Let's look at the crude birth rate per thousand. So you can see I'm on the Data World Bank. I'm looking at the U.S. birth rate per thousand, and now this is a lot of data, so it's more than we can really talk about. So what I'm going to grab is what happened in 1960, then I'm going to go to 1970, 1980, and then when you look at the bottom, it stops at 2019, so I'm going to use 2019 as my last value, but the rest I'm going to do in values of 10. So you can see I have 1960, 70, 80, 90, 2000, 2010, 2019. So like we did on the last one, we're going to change the years. So we're going to call this year 0, 10, 20, 30, 40, 50, and then remember this one didn't quite make it to 60, it's 59. So I'm going to start by putting in 0, 10, see how it goes 20, 30, 40, 50, and then we'll just change that 60 to 59. Our birth rates were 23.7, 18.4, 15.9, 16.7, 14.4, 13, and 11.4. We're going to hit zoom fit. And now we're going to try both a line and an exponential. I'll start with a line. y1, we have to hit our tilde. I say ax1 plus b. And then we'll also try y1 is approximately ab to the x1, and then hit that log mode. So let's look at our comparison. In both of them we can see that they have a negative relationship. I see the R is negative 0.9403, I see R is negative 0.9631. Now this time this 9631 is closer to negative 1 than the 9403, so we say this one definitely fits exponential. Our A is 21.8206 and our B is 0.98927. Let's write that back over so we can talk about the decay rate here. So let's do like last time. We're going to do 2 decimal places for A and we'll do 3 for B. So for A I have 21.82, and then B I have 0.989, and then that will be to the X. Remember when we talk about decay rate, we're going to do 1 minus 0.989, which is 0.011. So this would be our rate of decay for this exponential regression.